Welcome back, guys. Today we're going to be doing probability generating functions from the 9231 syllabus of further math AS and A level CIE board. So let's begin. The concepts that we're going to tackle today of PGS are these right here. So first we'll understand the fundamentals and then we will go to the specialized based questions. So these are the fundamentals. It's paramount that you need to understand these. So let's start off over here. Fundamentals. Questions will implicitly ask you to find the PGF. When I say implicitly, it means they won't give you your probabilities directly. That's what I mean. So first of all, you got to understand the question. We have 4 red balls in this case, 2 blue balls. Selecting 3 balls at random means that you would have at least 1 red ball. So that is one basic thing that you need to understand. So what I mean by n over here is the number of occurrences. For n equals 0, it means 0 occurrences, meaning 0 red balls. 1 meaning 1 red ball, 2 red balls, 3 red balls. So that's what I mean by n, and the probability that you're going to get 0, 1, 2 or 3 red balls is shown over here. How we calculate this probability is really simple. So using the basics of probability and statistics, we can see that it's 4 by 6 initially because there are 6 total balls and 4 of them are red, and without replacement, meaning that the next time you pick a red ball, the probability would be 3 by 5, and then if you pick another one, you're going to get 2 by 4 for the last. So you get a probability of 0.2. Similarly, we can do for each of these, and yeah, using the basic laws of probability and stats, you should be able to solve this easily and find out probabilities values. Next step is to find the PGF. So whenever we have one successful occurrence, we have t to the power of 1. If we have 2, we will have t to the power 2, and 3 will have t to the power 3. If we have 0, we have t to the power 0, which is just 1, so it doesn't matter. So to write the PGF when n equals number of occurrences, first write t to the power n for each occurrence. Since there are 4 possible occurrences, well, 0 isn't, we should write t to the power 0 plus t to the power 1 plus t squared plus t cubed. Next, we plug in each coefficient. So for t to the power 0, to have 0 occurrences of red would mean to have a probability of 0. So 0 times t to the power 0 is our probability here. For t to the power 1, to get 1 red ball, our probability was 0.2 as shown over here. And so 0.2 t to the power 1. Similarly, we do this for t to the power 2 and t cubed. You'll get this right here. And then to refine the function, we can just cut this part out because that makes absolutely no sense to include. And t to the power 1 can be written as just t. And so we get our refined PGF. So now you know how to calculate a PGF of any regular equation. So that is really good. But what adds on to the difficulty are the remaining parts of the question. So over here they ask us to find the PGF of y, when y is when you toss a coin and probability of obtaining a head is 1 by 4. When you toss 2 coins at the same time, number of heads is y. So judging by this, you can already see that the minimum number of heads you're obtaining is 0 and the maximum is 2, while you can also obtain a single head. So first of all, we have to calculate the PGF for this function. It is not too hard to do, so I'm going to leave this one to you, and the answer will be shown later. So now let's dig into part C, because part B we can do with the current knowledge of PGFs that we discussed in the fundamentals. So to do part C, it's to be the sum of red balls and the sum of heads obtained. This is part of the syllabus over here. Sum of independent random variables is the product of PGFs of those random variables. So as stated in the syllabus, it says it's the product. To sum up red balls and number of heads, we have to multiply our gx of t and gy of t. The reason being so is going to be explaining right now. So the maximum number of successful occurrences would mean to get 3 red balls and 2 heads, which is 5 success, and the minimum number would be to get 1 red ball, because there's only 1 red ball you can get here, and to get 0 heads for 1 success. So now we know that the power of t will be between 1 to 5 as shown, and that would be really simple. So to get 1 to 5, to have a t to the power of 5, we can't do any operation except multiply the two PGFs. And so our formula is derived. G is z of t. When z is the sum of observations x and y, our probability generating function of z will be the product of gx of t and gy of t. So when you multiply the two equations, you will get your gz of t, which is this right here. And also do note, if you have been attempting this PGF of y equation, this is the answer over here. We can use this and multiply with gx of t, and you can get this right here. Really simple, but to multiply it could cause a few mistakes. So what I do is factorize this and factorize this, and once I finish factorizing, I multiply them and then put them back in their denominators to get this. Any method is fine. There's no particular method that is right or wrong, but it's just less erroneous. Okay, so to do part D asks us to find the expected value and the variance. To find expected value, it's really simple. You just need to differentiate a function and then plug in t equals 1. For example, over here, if you differentiate, so first of all, you need to know the laws. Gx of 1 equals 1. What does this mean? It's really simple, and it doesn't just apply for x, it applies for y and z. It means that your original PGF, if you plug in t equals 1, you're going to get 1 no matter what. Let's test it out for the three of them we have right here. So if you plug in t equals 1, you get 0.2 plus 0.6 plus 0.2, which is 1. You plug in t equals 1 over here, you get 9 by 16 plus 6 by 16, which is 15 by 16, plus 1 by 16, which is 16 over 16, also known as 1. Same thing goes for here. 9 plus 33, 42, 42 plus 28, 70, 70 over 80 plus 74 plus 9 over 80 is 79 over 80, plus 1 over 80 gives us 80 over 80, which is 1. So this law holds for every PGF. Gx of 1 equals 1. Gx dash 1 equals expected value. What this means is that when you differentiate a function and plug in t equals 1, you're going to get our expected value. So that's how we find E of z. We differentiate this function, plug in t equals 1, and then get your expected value. So I'll let you figure this one out. And for variance, this is an equation where you have to double differentiate, plug t equals 1, and use this value and do this. So it may sound a little bit complex, but here's a simpler look. First of all, to calculate variance, you absolutely need your expected value. So here's the function that you can use to calculate variance of x, y, or z. It is to double differentiate the PGF and plug in t equals 1. Once you double differentiate it, we add it with our expected value we've calculated here, and then subtract it with our expected value, the whole square. That pretty much sums up variance of x, and that also sums up everything over here. We know how to use the concept of PGFs and construct PGFs. We know how to use formula for mean and variance, and we also know how to use the product of two PGFs to create a sum of independent variables, or PGFs. Now what we have to discuss is the specialized questions. These questions are typically a bit more complex, but they are just as easy to learn. Let's start with the type 1, which is discrete uniform distribution, as shown over here. So for this one, you gotta have a little bit of an understanding of geometric expansions. So let's first dive in. So the A part is asking to find the expected and variance values. That, using our knowledge in the fundamentals that we discussed here, you can solve this easily by just differentiating, plug in t equals 1, and going forward. But we don't know how to find probability of x equals 4. So how will we do that? We can't just plug in x equals t equals 4 and then get our value. That's not how it works. So first step is to factorize in the form of 1 divided by 1 minus x. So if you factorize this, you're going to get 1 by 3, 1 by 1 minus 2 by 3 t squared. You must understand that this is the sum to infinity for a geometric expansion. So if we go all the way here, you can see that the sum to infinity for a geometric expansion is a divided by 1 minus r. We know that a is the first term and r is the ratio. In this case, I write it as 1 by 1 minus x. Since a equals 1, it means our first term is 1. That is already confirmed. And what is x then means? So we have 1 divided by 1 minus 2 by 3 t squared. That is in the format of 1 by 1 minus x. Therefore, your x value will be 2 by 3 t squared. So now that we know that the ratio is 2 by 3 t squared and the first term is a, we can construct an expansion that goes like this. The first term is 1, and then we multiply by the ratio, and then ratio again, and then goes on until you get this right here. So now that we've expanded it, and remember we factorize 1 by 3. So step 3 is to finally solve. So first of all, to find the probability that x equals 4, it means to find the term with t to power 4, which is this right here. So is that probability the coefficient? Yes, but it is not exactly that straightforward, because 4 by 9 is the coefficient for t to the power 4, but we are forgetting that we factorized the 1 by 3. So 1 by 3 times 4 by 9, which is 4 by 27, is the coefficient of t to the power 4 as shown over here. And since the probability is directly affiliated with our coefficient, t to the power 4, which means x equals 4, probability would be 4 by 27. Therefore, you have your probability. It may sound complex, but with enough practice, it's easily doable. Next type is to do binomial distribution, and I used the worked example from a textbook for this question. So right here we have binomial 5, 0.2, meaning that there are maximum of 5 occurrences and the probability of each success or each occurrence is 0.2, which I call the probability of success. We'll label that as p equals 0.2, and q, which is the probability of fail, is 1 minus p, which is 1 minus 0.2, which is 0.8. So since x can take any value between 0 to 5, we make a table for x till 0 to 5. So instead of writing x, I'm going to write n, where n is number of occurrences, 0, 1, 2, 3, 4 and 5. So it is possible to fail every single time and get 0 occurrences. It is possible to fail 4 times and succeed once. And similarly, it is possible for each and every one of these. So to formulate the probabilities, we're going to have to use the binomial expansion formula. Using this formula, just directly plug in the values. This is the basics of further math, so you should know this. We can use and formulate this right here, and I'm going to now simplify the coefficients of the combinations. So we get 1, 5, 10, 10, 5, 1. This follows the binomial expansion as asked in the question, and it is a good way to structure the information like this as shown. So we know that a equals 0.8 or 0.2. It really wouldn't matter because it's addition. B equals 0.8, once again interchangeable, and n equals 5, which is the total number of occurrences possible. And we have the expansion over here, which does lead into the binomial expansion. But before we plug in, if we just plug in these values, you're going to get 1 to the power 5, which is 1, which makes no sense really, because we need to have t somewhere. So I said before, and I'll say it again, that every occurrence is affiliated with t, which means that if you have 0 occurrences, that means t to the power will be 0. And if you have 3 occurrences, means that the t power will be 3, so t cubed. And so for 5, you'll have t to the power 5. There is only one out of a and b, there's only one of them that's being multiplied as you go on with the number of occurrences. So you can see that 0.2 doesn't exist here, 0.2 increases, 0.2 has 2 now, 0.2 has 3, and so we can include 0.2t. So 0.2 times t, 0.2 t whole squared, and you can see that 0.2 is also increasing in powers as t is increasing in powers. So we have to reorganize our data as a equals 0.2t. So every occurrence of a increases the power to t. So a PGF would look something like this. Once again, interchangeable, you can put 0.8 and 0.2t. It really wouldn't matter as long as you get the final answer right. So that's for binomial distribution. It may seem a bit confusing as of now, but once again, enough practice means you're going to master this topic. Next up, we have geometric distribution. This is by far, I think, one of the simpler ones because this uses basics of geometric. So we have to know this formula right here, and it's okay if you don't understand it entirely because it is there in our list MF19 where you have this equation right here. This right here is our equation that we need to use. Since we have GOP, it's literally stated over here that we have GOP, and so we can use this equation right here. So we regard 1 minus p as q because it's explicitly stated over here. So I put it like that, pq to the power of n minus 1. Now that we've had our basic equation, now we have to have occurrences from n till, well, the maximum value. So for one occurrence, it would mean p to the power of p times q to the power of 1 minus 1, which is 0. So it's p. And since there's one occurrence, our t is to the power of 1, which is t. And therefore we can just keep incrementing it and we'll get this until we have this equation right here. So you can see how the sequence goes, and remember that n equals t. So for 3 occurrences, our power of t will be 3, and you can see that's how it's gonna happen every time. It's going to keep increasing like this. So for the first term we know it's pt. The second term, since there's a t being incremented, it means our ratio is qt. So our first term is pt, our ratio is qt. So you can see how this goes for every single until it reaches n, which is the maximum number it's possible. So we call this sum to infinity. Okay, so if we were to add all of this, to find the sum to infinity, we can use this formula once again, where we found our first term to be p times t, so pt, and our ratio to be qt, because qt is being multiplied every single time for the next to next, and our ratio is qt as stated over here. Plugging them in, we get pt divided by 1 minus qt, which is exactly what the question asks of us, which is this right here. And there you go, 3 marks, free 3 marks just for you. And the last type of question, the specialized questions, I'd say, is Poisson distribution. So I couldn't find the past paper question, so I used the textbook's definition, and it's really good. So find the PGF of this. So we know that the Poisson distribution has this formula right here. If they don't state it, you can still use it over here. Okay, instead of r factorial they have it as x, but it doesn't change anything. So when x equals 0, you're going to have this, x equals 1, you're going to have this. So you just need to plot a table first of all, and I will explicitly state that this was taken from the CIE textbook of Martin Crozier and Lee McKelvey. Okay, now when x equals 1, 2, 3, you can see how it's going on. You can see what's going on as well. So if we were to add them all up, you're going to get this over here, and it goes on till infinite. And therefore now if we factorize e to the power of negative lambda, we're going to get this equation right here. Now it is paramount to understand that this is a Maclaurin series, and if you can see over here from the list of MF19, if you don't believe me, it's shown in further pure math, I think. Yeah, the Maclaurin series, if you look over here very carefully, you can see 1 plus x squared by 2 factorial and so on. That corresponds with this over here. So over here we have x lambda t, x squared lambda t squared. You can see the correlation between the two, which means that our x value is lambda t. Okay, now using this we can factorize e to the power x. What was x? Lambda t. So we can sum this up into e to the power of lambda t. So we get this right here. Now once again, using the law of indices and factorization, you can get your lambda factorized. So we have e to the power of negative lambda plus lambda t, and if you factorize lambda, you're going to get this right here. So our PGF will be this over here, and it's really simple to do. And that pretty much sums up all of PGFs. Obviously these concepts are going to use up our fundamentals. Each question will build up on a fundamental, so it's crucial that you learn these, and then specialized questions, they just develop further knowledge on PGFs. But otherwise this topic is really simple and straightforward, and with enough practice it's going to be a free 10 marks in whatever they ask you. So I hope you enjoyed this video. Thank you for watching. The next video will probably be on non-parametric tests, so I'll catch you then. See you.